like, quickly, like 5 minutes.
5 minutes.
All right, so basically our project was like we got a problem of trying to determine where a sound was saying. So pretty much if you make a sound over here, it can tell you where the sound is identically. So what we did was we started with the regular patch, and then we slowly evolved into this type of patch, which we imitated the middle canals off of the ear canal, and we use HFSS to see if the antenna actually works and propagates, which means it does work since the operating frequency is shown between 1 and 2 VSWR, and it's also almost ideally matched. Then we took it into console to see what the pressure ratings would be on the outside. And so here you can see the capillaries are right here, and then we found out that all within the cochlear canals actually give better pressure ratings than it does with just air. And then we move on to the transducers, which are placed on the outside of the actual patch.
Right, so as Joshua was saying, we wanted to look at the pressure readings on the outside of these cochlear canals. What they're doing is they're serving as waveguides. And the reason we're interested in those pressure readings is because we're actually going to take those pressure readings, find the time of arrival that the propagating signal arrives at those sensors, and using that time of arrival, we're able to throw it into a time difference of arrival algorithm. In this case, we're using a system of 4 equations, and we're actually able to use exact substitution. So this kind of algebraic approach makes for a very fast implementation, and then what we did is we took that and we moved it into LabVIEW itself. So what we're running is a LabVIEW code that's able to take these time of arrival signals on the end of these waveguides and actually figure out where the localized sound is coming from.
Oh yeah, we actually have this. So this is the actual fabricated antenna. It is really small.
It shows that it is operating at 3 gigahertz. This is a VSWR plot. Oh, this is the actual antenna.
So actually model this one. Yeah, because this right here is the ideal case, but in reality you have to add like extra length and or extra width in order to get it to the right point. But it gives you something to start with.
Other questions?
I don't understand what it's actually telling you.
Oh, I mean, this is the VSWR plot.
This is a network analyzer.
Yeah, this is showing the operating frequency of the antenna. Yeah. And so, as long as it's between 1 and 2, you have an active antenna. And so, right here, this is at 1.96. This is there's kind of varying impedances in the air. And so, like right now, it's like yesterday when we ran this upstairs. And so, it could be there's a possibility it was running at 1.76, which is much better, like in between, in relation to your gap between 1 and 2. Right now it's reading 1.96. However, that just tells you that your antenna is active, and like I said, this is just showing that it's at your 3 gigahertz range. So it is operating at the desired frequency.
Where does your algorithm run? Are you doing it post-processing on a host computer somewhere?
Yeah. You mean to
Right now, yes. But what this algorithm is based on is a VHDL implementation that they use some C++ code to test it with. So what I did is I looked at the test bench and I said, okay, I'm gonna take that test bench and I'm gonna pull from it, and I see you're from National Instruments, so you're probably familiar.
I should have worn a different shirt. I'm just curious, just overall, where's the algorithm running now, and what's the intended platform?
Yeah. So right now it's going to be running post-processing on a host PC, on a machine, and then eventually what we'd like to do is kind of get it down into something much smaller.
Like an FPGA?
It could run on FPGA. Especially since it's a VHDL model, you can throw it on the Spartan boards that are in the computer labs in there. You can throw it on. I think even something as simple as a microcontroller and a PIC can probably run this thing. It's direct substitution, so we're only dealing with algebra. So there's no kind of advanced mathematical functions that we really have to work with here, other than a square root, squaring things, which is just iterative multiplication, which could require additional RAM for the microcontroller. That kind of be, I guess, a caveat of the implementation here. But you're able to go with really small things, which is good. And because it's direct substitution, there's no iteration. There's no for loops or anything like that. So it makes for very fast, which caters to the smaller, less powered hardware.
Yeah. So the goal would be to put it on some type of related target.
Right, or even something that somebody can wear, something that even as local as that.